Alright, hello. So today we're talking about polar coordinates, and our first question is what does it mean to be two-dimensional? Right, and the answer here, the answer is that in order to locate something, you need two pieces of information. Right, so I'll say here that we are used to locating points in a two-dimensional plane using Cartesian coordinates. And Cartesian coordinates just means x and y, right? So what we do here is fix an origin at the point 0, 0. And we say that we have x comma y. Those are the two pieces of information we use to locate things. And here, what we can write is that x is the direction left or right from the origin, and y is going to be the direction up or down from the origin. Right, so that's how we're used to just describing the location of points on a plan. But we actually have another way. So I'll say here another way of locating a point in two-dimensional space is with polar coordinates. Right. So here with polar coordinates, instead of x and y, what we're given is r and theta. So r is going to be our radius. So r is our radius, meaning how much do you go out from the origin. And theta is going to be the angle, meaning how much you go around. Right, so what we mean here is, let's say we just draw our coordinate system, right? So we can say, let me just draw some circles here, just to make it a little bit clearer of what I'm talking about, right? So we can say we've got a radius. So let's say we have a point here. Let's say we've got a point P, which has a radius and a theta, an angle theta associated with it. So the radius is the distance from the origin to P. So this here, this distance is our radius. And the radius is just the radius of the circle that the point is lying on, right? So if you look from this origin out to the point lies on a circle, right? So this doesn't have to be doesn't have to be a nice circle. It can be a circle of radius, I don't know, square root of 2, for instance. But the point lies on some circle that's centered at the origin, and you can say the radius of that circle. So that's one piece of information, the radius. And the next piece of information we know is the angle. So here, this is our angle, theta, from this axis. And we're going to call this axis the polar axis. Right, so as long as we know this radius, i.e. the distance from the origin, and the angle that it makes, this line makes, with the polar axis, or in this case the positive x-axis, then we can describe exactly the position of the point. So instead of having to use x and y, we can now use r and theta. Okay, so I'll write down what I said there. So we're going to fix a pole called, and we called it O, which is the usual origin. Right, so we're going to call the origin, we're going to call that a pole. And fix the polar axis. Right, so the polar axis is just the axis from which we're using theta, right? So we're using theta from this axis going counterclockwise. That's our angle theta. And I'll say here, we provide a direction and a distance. Right, so these are the two things. So here, r is the distance from O to P. And second thing here is that theta is the angle between the polar axis and the line OP. Right. Okay. So one thing that I should note here before we move on is that r can actually be negative. So I'll write here, note that r can be negative. Right, so here our rule is that point r comma theta represents the same point as point negative r comma theta plus pi, right? So if you're given a point with a negative radius, all you have to do is make that radius positive and then subtract pi or add pi to the angle. Notice if you add pi, if you add 180 degrees, that's the same thing as subtracting 100, sorry, should go the other way around. If you add 180 degrees, that's the same thing as subtracting 180 degrees, because you end up at the same spot, right? So all you have to do, if you have this negative radius, is you have to either add or subtract pi radians, which is 180 degrees, to get to this angle here. And now you can write it without that negative sign in front. So that's how we're going to deal with that. And The second thing I'll note here is that positive theta is going to be corresponding to a counterclockwise rotation, and negative theta is going to correspond to a clockwise rotation. Right, so that's just how we were doing trigonometry anyways, right? We were saying if we've got a positive value theta, then you take the angle going from the positive x-axis towards whatever point you had, right? So you take this to be a counterclockwise angle, but if the angle is negative, then all of a sudden you take it to be clockwise. Okay. So let's actually do an example with this, just to see how we can plot these points. So example number 1 is going to say plot the polar points, and part A is going to be 1, 5 pi over 4. Part B is going to be 2, 3 pi. Part C is going to be 2, negative 2 pi over 3. And part D is going to be negative 3, 3 pi over 4. Okay, so we've got to plot all of these points. So that's our goal. So to do that, let me go ahead and draw our coordinate system. And notice here, these are radius values. Remember, we have r comma theta, right? So here the radius is 1, 2, 2, and negative 3. So I'm just going to go ahead and draw for us 3 circles. So this is going to be a circle of radius 1. This is going to be a circle of radius 2. And this is going to be a circle of radius 3. Right? So we know that this point has to lie somewhere on the circle of radius 1. These 2 points have to lie somewhere on the circle of radius 2. And this third point has to lie somewhere on the circle of radius 3. Now, exactly where it lies on the circle is exactly determined by this angle theta that tells us where it lies on the circle, right? So again, this is our polar axis. So we consider theta going from this axis. So the first one is 1, 5 pi over 4. So it lies on this circle of radius 1, and the angle is 5 pi over 4. So if you had 4 pi over 4, that's pi, or 180 degrees. So that would get you over to here. That would be pi. But so that would be 180 degrees, but you're adding pi over 4. So you're adding an extra 45 degrees. So you're actually going to go to here. And now this is going to be your point, because notice that angle that I drew was 5 pi over 4, and we said that it lies on the circle of radius 1. So this is going to be our point. Right, so I'm going to erase all of this just to make it a little bit less sloppy for us. But this is going to be the point in A. Right, so that's point A. Now let's do point B. So point B says 2, 3 pi. It lies somewhere on the circle of radius 2, and the angle is 3 pi. So 1 pi, that would be 180 degrees. Another pi would get you back to where you started, because that would be 360 degrees. Then we're going to add, sorry, that would be out here. Then we're going to add another 180 degrees to get out to here. Right, so we started here. If you add 2 pi, you get back to here. If you add another pi, you get to here. And this would be B. Okay. Now our third point is going to be 2, negative 2 pi over 3. So now we have a negative angle. So if you converted that to degrees, it can sometimes be more helpful just to kind of get an idea of what's going on. That would be negative 120 degrees. So you start from this axis and you're going to go clockwise this time, because you have a negative angle. You're going to go clockwise 120 degrees. So if you do that, notice this is on the circle of radius 2. if you do that and you go clockwise that angle, you're going to get somewhere around here. And this would be C. Right, so that's going clockwise 120 degrees. And now this angle here, notice this has a negative radius. I said we want to convert that to an angle with positive radius. We always want to do that. So what we can do is go ahead and add pi. Okay. So we need to add pi, right? And if we add pi radians, then what we're going to get, so if you subtracted pi instead, you would get, so notice if you subtract pi, I was a bit confused as to why this didn't work out at first in my head, but no, if you subtract pi, you're subtracting 4 pi over 4, so that's minus pi over 4, which is actually the same, it's going to get you to the same place as 7 pi over 4. So let's look at where 7 pi over 4 gets us. We're on the circle of radius 3, and we're going 7 pi over 4. So notice that 6 pi over 4, that's almost at 2 pi. That gets you to here. So you're going from here all the way around to here. That would be 6 pi over 4. And now 7 pi over 4 would land you there. So that would be D. Right. So again, just going back and learning our trigonometry, learning back to the unit circle. The unit circle is very helpful for all of this, but just kind of navigating our way around the circle, that's how we get what we need in order to plot these 4 points. Okay. So something I should note here. So note. So we're done with the example, but something I'll note here is in Cartesian, it's supposed to be a capital C. In Cartesian coordinates, every point has exactly one representation. Right. But in polar coordinates, it's different because every point has infinitely many representations. Right, and to see why that's the case, well, notice if we added 2 pi to any of these angles, we would get back to the same place, so we'd have the same point, right? So if we added or subtracted 2 pi some number of times, so let's say we wanted to add, I don't know, 20 times pi, well, we would get back to the same place as if we had had this point to start with, right? So there's infinitely many ways to write this point, but they all give you the exact same location, which would be this location here in part D. Okay. So our next topic is the fact that we want to relate these polar coordinates to Cartesian coordinates, because we want to be able to go between the two. So let me just erase this. So I'll say here relating polar and Cartesian. Okay. So let's look at what's happening here. We've got, let's say we've got our point here. This is our point P, which has a radius and an angle theta associated with it. So we know that this is going to be our radius, R, and this is our thing, our angle theta. And we know that we can also write this point as x comma y. So we know that this distance here must be x, and this distance here must be y, because we could also write our angle as x comma y instead of r comma theta. Okay, now let's just go ahead and use a little bit of trigonometry here. cosine of theta. Remember we had the acronym SO, CA, TOA. Well, cosine of theta is adjacent over hypotenuse. So adjacent over hypotenuse, it's x over r. And similarly, we're going to get that sine of theta using the acronym as opposite over hypotenuse. It's going to be y over r. Okay, so here our answer to this issue is to convert polar to Cartesian. All we have to do is say that, well, if we multiply both sides by r, x is equal to r cosine theta, and y equals r sine theta. Right, so that's very useful, right? Because as soon as you have some kind of Cartesian equation, then you can just plug in these values for x and y, then you actually get an equation that's in terms of polar coordinates. Okay, and let's say we want to go the other way. Let's say we want to convert our Cartesian coordinates into polar coordinates. Then what we're going to have to do is say that, well, we know that x squared plus y squared is always going to be equal to the radius squared. So we can use that fact, and we can also use the fact that tangent theta, if we look at here, it's opposite over adjacent, so it's going to be y over x. Right, so we can use both of these facts to say if we are given something, I think I spoke the other way around at first, but if we're given something in Cartesian, we can convert it to polar using this, and if we're given something in polar, we can convert it back to Cartesian coordinates using this. I think I said it the wrong way around at first, but those are the directions that we're going to use. Now, let's do an example. Example number 2. It's going to say convert the point 2 comma pi over 3 from polar to Cartesian coordinates. Right, so we're going from polar to Cartesian, so we use these two. Okay, so we know that x equals r cosine theta. We're already given what r and theta are, so we can just plug those in. 2 cosine of pi over 3. Now, let me draw the unit circle here. I'm not going to keep drawing this, but I'm just going to draw it once so that we can remind ourselves of how we can draw it. Right, so the unit circle is very useful because the x values are the cosine values and the y values are the sine values. So the way we draw the first quadrant of the unit circle is by going 1, 2, 3, then 3, 2, 1. Take the square root of everything. The square root of 1 is just 1. Divide everything by 2. And turn everything into a point. And now those are our coordinates, and we know that this is the angle pi over 6, this is pi over 4, and this is the angle pi over 3. And then we can just read off, because the x values on the unit circle are cosine theta, and the y values in the unit circle are sine of theta. Okay, so now we're trying to find cosine of pi over 3. So we look at the angle pi over 3 and we look at the x value. That's 1/2. So that tells us our answer there. So this is 2 times 1/2, which is equal to 1. And now we just need to find the y value. So y equals r sine theta, which is 2 sine of pi over 3. And again, the sine value is, the value of sine is going to be the y value. So we look at the y value of pi over 3, that's root 3 over 2. So it's 2 times root 3 over 2, which is going to be root 3. Okay, so in collection, this was our x value and this was our y value. So our point is actually going to be 1, comma, root 3. That's our answer. Right, so this was polar coordinates. Now this is Cartesian coordinates. We've converted it. Okay, and part B is going to be just to go the other way. Right? So let's write that down. Okay. Part B says convert the point 1, negative 1 to polar. Right, so this is actually already in Cartesian coordinates, so this was our x comma y, and we need to convert that into polar, and it says to go from Cartesian to polar, we need to use these two equations here. So, the first one is that x squared plus y squared is going to be equal to r squared. So what that tells us is if we plug in x and y, we're going to get 1 squared plus negative 1 squared equals r squared. So 2 equals r squared. So r equals plus or minus root 2. But we can always just choose this to be positive, right? Because remember, we can convert a negative radius into a positive radius. So we might as well choose our radius to be positive root 2. Okay. All right, so now we need to use our second equation. We use the fact that x squared plus y squared is r squared, but now we need to use this equation. So it says tangent theta is y over x, that's negative 1 over 1, which is negative 1. Right. So using this equation, we get that tangent theta is equal to negative 1. And now, if you look at where tangent theta is equal to 1, that's when theta equals pi over 4, but it's negative 1. And if you look at what quadrant you're in quadrant 4, because this point is in quadrant 4. So that tells us here that theta actually equals negative pi over 4, or 7 pi over 4. Notice both of those two angles get you to the same place, because if you add 2 pi to this, you get to this, but either one gives you the same answer. So our answer is root 2 comma negative pi over 4. So if we convert our point into polar coordinates, this is our answer. Or we could just add 2 pi or subtract 2 pi some number of times. So let's say that another answer would be root 2 comma 7 pi over 4. Right? So both of these answers are fine. They both give us the same point, because if you add 2 pi to this angle, you get this angle. So you don't even have to say both of these, you can just say this one. This is a sufficient answer. Okay, so the last topic for this section is going to be polar curves. And these things, I'd say the best way, if you're asked to figure out what one of these equations gives you, a lot of the times the best way to do that is just to start plotting points. And we learned how to plot polar points, so we can just do that if we have to figure out what one of these looks like. But let's go through it. So I'll say here polar curves. The graph of a polar equation r equals f of theta, or sometimes you'll see written capital F of r theta equals 0 consists of all points P that have a representation r comma theta whose coordinates satisfy the equation and example number 3 is going to say for A, what curve is satisfied by the polar equation r equals 2. Right, so the equation here that they give us is r equals 2. And the thing to notice about this equation is that we have no theta. So theta can be anything. Because they didn't say that r relates to theta in any way, they just said that r equals 2. So if you go ahead and plot all of the points that are a radius 2, we said the angle doesn't matter, just all of the points that are a radius 2 away from the origin, you're going to get a circle. So our answer is going to be a circle. So we'll say here the curve is a circle of radius 2. Okay. Now, part B. It's going to sketch the polar curve theta equals pi over 6. That's kind of a poor 6. Okay, so the polar curve theta equals pi over 6. So again, I'd encourage you to think about what this should be. But if theta equals pi over 6, notice it doesn't depend on r. So r can be anything, including negative. So we're just taking all the points that are at an angle of pi over 6 from, or an angle of pi over 6, which is an angle of 30 degrees from this polar axis, I think that's what we call it, right? So just an angle that's all the points that are an angle of 30 degrees away from that. So if you just take all of those points, and that's going to be these points here, but also notice that r can be negative, so it'd also be these points here. And you end up getting a line here at an angle of theta equals pi over 6 from the polar axis there, right? So you end up getting this line, right? Because it's just all the points at an angle of 30 degrees away from this axis, and it doesn't matter what the radius is. So that's your answer there. Okay, now, so as I said, so you can kind of just figure out what those ones are, but some of the other ones, they kind of get a bit complicated. So the easiest way to figure them out is just to start plugging in values of r and theta. Just plugging in values of theta to get points. That's what I meant to say. So if you pick a value of theta, then you're going to get some point coming from that, and just pick different values of theta, and that'll give you points on the curve. So part C is going to be r equals 2 cosine theta. And again, I said just pick values of theta, plug it in, plot the points that you get, and eventually what you're going to come out with is going to be a circle of radius 1 that's centered about this point here. So it's centered about the point 1, 0, and it's a circle of radius 1. Okay. The next one, part D, is going to be r equals -4 sine theta. And again, you just pick different values of theta, plug it in, get points that are of the form r comma theta, plot those points, and eventually what you get is going to be a graph, and your graph is going to be centered at y equals -2, this point 0, -2, and it's going to be a circle of radius 2. Okay. Part E is going to be the equation r equals 3 cosine of 2 theta. So again, if you just plot points, eventually what you're going to end up getting, and these graphs can get a little bit complicated, but this graph is now going to look something like this. Something where you've got like these 4 petals. And let's say just our last example here is part F. If r equals 3 cosine of 3 theta, you just start plugging in different values of theta, and you're going to get a graph that looks like this. So that would be your answer there. Okay. Now, I might have said that was the last topic, but actually our last topic, or rather, I've just got one more example, is what I meant to say. But before I write that example, let's just write down a summary of the equations that we need to use in this section to convert equations. Okay. I guess I'll erase this as well. Okay. So, for converting equations, what we're going to need to use is the fact that x over r equals cosine theta, y over r equals sine theta, x squared plus y squared equals r squared, and lastly tangent theta equals y over x. Okay, so exercise number 4 is going to say convert the equation x squared plus y squared equals 2y into polar. Alright, so we need to get rid of the x's and the y's and start introducing r and theta. Now, x squared plus y squared, we already see we can replace that with, x squared plus y squared, we can replace that with r squared. So, what I'll write here is x squared plus y squared equals r squared. So, r squared is going to be equal to, so here this is r squared, is equal to 2y. And now you can divide by 2 on each side, so 1/2 of r squared equals y. And we already know that, well, I mean, we didn't have to do that yet, but let's plug in what y is equal to. So y is equal to r times sine theta. So 1/2 of r squared equals r times sine theta. And notice here we just want r on one of the sides, and normally we don't want to divide by variables because the variables could be 0, but we're going to go ahead and assume our radius is not 0. So I'm going to divide both sides by r, which is sometimes bad to do if the variable can be 0. But let's just say we can divide both sides by r. So we get 1/2 of r equals sine of theta. And now we can multiply yeah, okay. Well, I didn't need to divide both sides by 2, but anyways, you put the 2 back on the other side, and you get that r is equal to 2 sine theta. That's what we were looking for. Okay. So here I'll say that the way we got between these two steps is the fact that y equals r sine theta, and we just went from there. Okay. So the next part B, is going to say find a Cartesian equation for r equals 2 cosine theta. Okay, so notice we've got something, we've got an r, and we need to replace the thing with theta as well. So we're going to use these equations to help us. So we know that cosine theta equals x over r. So we can replace that there. So if we replace that there, then we get r equals 2 times, we replace cosine theta with x over r. And we can multiply by r on both sides. R squared equals 2 times x. And now, well, r squared, we actually know how to get rid of that as well, because r squared equals x squared plus y squared. So x squared plus y squared equals 2x. Okay. And now we're trying to, how should I say this? We're trying to solve for the equation of a circle in standard form. So the way we do that is subtract by on both sides by 2x. So we're going to subtract 2x on both sides, because we want all the x's and y's on one side, and we want the right side to be equal to a number, right? Because that's the equation of a circle. And for the equation of a circle, we have x minus h squared plus y minus k squared equals r squared, right? So that was the equation of the circle. But notice we're going to have to somehow, I don't know, mess around with this term here to get it to actually be equal to x plus or minus something squared, right? So the way we do that is by what's called completing the square. We need to add something to both sides to make this look like this. And the way we do that is we need to add 1 on both sides. Add 1. Right. And the reason we're doing that is because now we have x squared minus 2x plus 1 plus y squared equals 1. But now this thing here looks like something we can factor. That's the reason we added 1 to both sides. Because now we can factor this, and this actually looks like x minus 1 squared plus y squared equals 1. Right. So now this is a circle of radius, right? So if you look at the radius here, this is, so the square root of this number is the radius, so the square root of 1, which is 1. It's a circle of radius 1, centered at, so this is going to be the equation of a circle that's centered at h, comma k. So here h is actually equal to 1. So this is centered at 1, comma 0, because here k is 0. So this is the equation of a circle of radius 1 that's centered at 1, comma 0. Okay, so that's how we would start with an equation in polar coordinates and convert it to an equation in Cartesian coordinates. And now this equation, we notice, is a circle.